Retrograde Venus. It spins backwards. Its runaway greenhouse effect is a direct warning for Earth's future. Venus is the second planet closest to the Sun and one of the most massive bodies in the inner solar system. With a diameter of about 12,100 kilometers, it is only slightly smaller than Earth. Its atmosphere is extremely dense, with a chemical composition dominated by carbon dioxide. The pressure on the surface is about 90 times greater than that of Earth. This makes it one of the most hostile environments known. Venus's rotation presents an anomaly. The planet spins in the opposite direction to most other bodies in the solar system. This motion is called retrograde rotation. While most planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. Furthermore, its movement is extremely slow. A single day on Venus lasts about 243 Earth days. The origin of this retrograde rotation is still not fully understood. One of the most accepted hypotheses suggests that collisions with massive bodies during the planet's formation altered its rotational axis. Another possibility involves gravitational interactions and tidal effects with the Sun. Dynamic models also evaluate the influence of its dense atmosphere on rotational evolution. No theory is conclusive so far. Despite being farther from the Sun than Mercury, Venus has the highest surface temperature among all planets. This is due to its thick atmosphere, which produces an intense greenhouse effect. Solar radiation penetrates the clouds and heats the surface. The heat generated is trapped by CO2, preventing cooling. The average temperature exceeds 460 degrees Celsius. The Venusian atmosphere is composed of about 96.5% carbon dioxide and 3.5% nitrogen, with traces of sulfur dioxide and other compounds. Thick clouds of sulfuric acid cover the planet. These clouds reflect most visible light but allow infrared radiation to pass through. This structure reinforces the efficiency of the greenhouse effect and generates extreme thermal stability. The atmospheric pressure on Venus's surface is equivalent to that found 900 meters deep in Earth's oceans. This poses a severe technical challenge for robotic exploration. Most probes sent have only lasted a few hours in operation. The Soviet Union's Venera 13 lander was one of the longest-lasting, recording data for about 2 hours. Despite the extreme conditions, there are signs of recent volcanic activity on Venus. Studies of infrared emissions and variations in sulfur dioxide suggest that the planet may still be geologically active. Radar-based orbital models indicate structures resembling lava domes and calderas. Direct confirmation of this activity is still underway. Venus does not have a global magnetic field like Earth's. However, its dense atmosphere interacts with the solar wind, forming a magnetotail, an elongated region of plasma that extends away from the Sun. This tail was detected by probes such as Venus Express. It shows how the atmosphere can act as a shield even without an internal magnetosphere. In the upper atmosphere, winds reach speeds exceeding 300 kilometers per hour. This layer rotates around the planet in just 4 Earth days. The phenomenon is known as atmospheric superrotation. Its origin is not completely understood, but involves interactions between solar radiation, convection, and thermal tide dynamics. The contrast with the slow surface rotation is striking. There is evidence that Venus may have had liquid oceans in its distant past. Climate models indicate that with lower insolation and different levels of carbon dioxide, the planet could have maintained liquid water for hundreds of millions of years. Isotopic data from the current atmosphere support this hypothesis. The disappearance of these oceans is still under investigation. Currently, several missions are in development to study Venus in more depth. NASA's Veritas mission aims to map the surface with high-resolution radar. Meanwhile, ESA's Envision mission will seek to understand the interaction between Venus's interior, atmosphere, and geology. These projects are expected to expand knowledge about the planet's thermal and tectonic history. Enceladus, moon of Saturn that ejects plumes containing water and organic molecules, may harbor life. Enceladus is one of Saturn's mid-sized moons, with a diameter of about 500 kilometers. Despite its small size, it became one of the most studied bodies in the solar system after the discoveries made by the Cassini probe. Its surface is composed almost entirely of water ice. Observations reveal extremely high reflectivity, indicating low contamination by dust or dark material. This makes Enceladus a highly bright object, with an albedo greater than 0.9. The main feature that makes Enceladus extraordinary is the water vapor plumes emerging from its south polar region. These plumes were first detected in 2005 by Cassini. They originate from linear fractures called tiger stripes that cut through the frozen crust. The expelled material reaches hundreds of kilometers in altitude. Some of it escapes into space and contributes to Saturn's E-ring. Spectral analyses of these plumes revealed the presence of simple organic compounds, such as methane, carbon dioxide, and traces of ammonia. Silica particles and salts were also identified, indicating interaction between liquid water and rocks. This suggests the existence of a subsurface ocean in contact with a rocky core. That interface is considered a favorable environment for the synthesis of complex compounds. Geophysical models indicate that Enceladus's interior contains a global ocean beneath the ice crust. The thickness of the crust varies, being thinner near the South Pole. The presence of sufficient internal heat to maintain liquid water is attributed to tidal effects. Gravitational interaction with Saturn and other moons causes periodic flexing that generates friction and internal heating. The emission rate indicates continuous and stable activity. This allowed Cassini to make multiple flybys through the active region. On some occasions, the probe passed directly through the plumes, collecting samples of particles and gases. These data provided some of the most direct evidence of a potentially habitable environment beyond Earth. Enceladus became a top priority in astrobiology. Studies on the pH and chemical composition of the ocean suggest an alkaline environment, with properties similar to hydrothermal vents on Earth's ocean floor. On Earth, these regions are inhabited by microbial communities that do not depend on sunlight. This strengthens the plausibility that microorganisms might also exist on Enceladus, using chemical sources of energy. There has been no direct detection of life so far. However, the methane present in the plumes has raised hypotheses about its origin. It may be produced by geochemical processes, such as serpentinization, or by biological activity. Laboratory experiments and simulations aim to distinguish these possibilities, but results remain inconclusive. Future missions may search for more specific biosignatures. Beyond the astrobiological interest, Enceladus provides valuable data on the thermal dynamics of small icy bodies. Its activity challenges models that predicted moons of this size to be geologically dead. This led to a re-evaluation of habitability criteria. The concept has expanded to include icy worlds with internal energy sources. Proposed missions like the Enceladus Orbilander aim to conduct extended and precise analyses of the plumes. This mission intends to orbit Enceladus for several months and then land near the active fractures. The goal is to study the internal structure, ocean chemistry, and possible biosignatures. This will require highly sensitive instruments and systems resistant to radiation and extreme cold. The study of Enceladus also influences the engineering of cryogenic probes. The ability to operate an icy environment with dynamic activity is essential for missions to other similar worlds. Interaction with active plumes demands protective shielding and precise navigation strategies. Lessons learned from Cassini serve as the foundation for these future missions. Enceladus is constantly compared to Europa, a moon of Jupiter that also has a subsurface ocean. However, Enceladus offers more direct access to internal material through its plumes. This makes it more accessible for indirect exploration of the ocean without the need to drill through ice. This logistical factor directly influences priority choices in planetary astrobiology. The potential of Enceladus as a habitable world remains among the most promising in the solar system. The presence of liquid water, energy, and organic compounds places this small moon at the center of future strategies in planetary science. Io, moon of Jupiter with extreme volcanism, helps us understand violent geology and the exploration of active worlds. Io is Jupiter's third-largest moon, with an approximate diameter of 3,640 kilometers. It was discovered by Galileo Galilei in 1610 and is one of the 4 Galilean moons. Its interior is composed of silicate and iron, with a crust rich in sulfur and sulfur dioxide. Its yellow and reddish coloration comes from these compounds. Visually, Io stands out for its highly irregular surface. What makes Io unique is its extreme volcanic activity. It is the most geologically active body in the solar system with hundreds of volcanoes. Many of these volcanoes are active, releasing basaltic lava and gas plumes that can reach altitudes of 400 kilometers. The source of heat for this activity is not residual internal energy, but tidal heating. The gravity of Jupiter and its neighboring moons creates internal flexing that generates heat. Tidal heating on Io results from its slightly elliptical orbit maintained by gravitational resonances with Europa and Ganymede. These interactions keep the body constantly deformed and prevented from cooling completely. The generated heat is sufficient to maintain active magma chambers beneath the crust. The constant release of molten material frequently renews the surface. Images captured by the Voyager, Galileo, and Juno spacecraft reveal vast lava plains and calderas up to 200 kilometers in diameter. The absence of impact craters indicates that the surface is continually recycled. Some regions display recent lava flows with temperatures above 1,600 degrees Celsius. Io's geological dynamics offer a unique opportunity to study volcanism on a planetary scale. Plumes of sulfur and sulfur dioxide ejected by volcanoes such as Loki Patera and Pele contribute to the formation of a thin temporary atmosphere. This material also interacts with Jupiter's magnetosphere, feeding the plasma torus surrounding the planet. The interaction between Io and Jupiter's magnetic field generates intense electric currents. This influences the electromagnetic environment of the region. Exploring Io presents significant technical challenges. The intense radiation from Jupiter's magnetosphere makes operating spacecraft in Io's orbit particularly complex. However, future missions like the Io Volcano Observer (IVO) are under study. This mission plans to conduct multiple flybys to analyze volcanic dynamics in detail. It will include spectrometry, radar, and thermal imaging. Studying Io also provides models for understanding the thermal behavior of exomoons. The combination of tidal gravity, internal heating and material release could apply to bodies beyond the solar system. Additionally, it allows scientists to test hypotheses about geological evolution of extreme worlds where heat originates not from radioactive decay, but from active gravitational interaction. The constant presence of volcanic activity creates a natural laboratory for analyzing high-temperature silicate reactions. This contributes to modeling internal differentiation processes and heat transport. The composition of the plumes provides data on the chemistry of the mantle and crust. Such information is useful for comparisons with rocky planets like Earth and Venus. Io also affects the space environment around Jupiter. The charged particles released during eruptions are captured by Jupiter's magnetosphere. This process creates an extremely hostile radiation environment for spacecraft and satellites. Studying this interaction helps in understanding planetary magnetospheres and interstellar plasma. It is an example of how active moons can influence larger systems. Data obtained from Io also help predict how volcanism can affect a planet's atmosphere and climate. Although Io doesn't retain a dense atmosphere, the physical principles behind gas release are similar. This includes plume dynamics, particle distribution, and chemical recombination in high-energy regions. These studies are fundamental to comparative astrophysics. Computational models simulate Io's thermal evolution over billions of years. They show that the body likely maintains its activity thanks to the stability of its orbital resonance. This supports the idea that tidal heat can be sustained over long timescales. Such stability is also sought in exoplanetary systems with moons orbiting gas giants. Ceres, bright spots. Dwarf planet with subsurface brine, potential space refueling station. Ceres is the largest object in the asteroid belt between Mars and Jupiter, with a diameter of about 940 kilometers. It was classified as a dwarf planet in 2006, alongside Pluto. Its shape is spherical, and its composition includes a mixture of rock and ice. Observations by the Dawn and Hubble missions revealed a relatively dark surface. However, certain regions drew attention for reflecting more light than expected. These regions are known as bright spots and are especially concentrated within the Arrokoth crater. High-resolution images from the Dawn spacecraft showed that the spots are not uniform. They display internal structure with centralized deposits and surrounding fractures. Spectral studies indicate that the material is primarily composed of hydrated salts such as sodium carbonate. This points to recent geochemical activity. Geothermal models suggest that there is a layer of liquid brine beneath Ceres's crust. This brine may be connected to larger reservoirs at depth. The heat required to keep the brine liquid may come from the radioactive decay of elements within. There is also evidence of thermal conduction facilitated by salts, which lower water's freezing point. This could explain the periodic release of fluids to the surface. The presence of salts and liquid water implies that Ceres may still have moderate internal activity. The bright spots appear to be deposits left by this liquid as it reaches the surface and evaporates. The rate of change in reflectivity over time has been measured by Earth-based telescopes and by Dawn. These variations suggest the processes are relatively recent on a geological timescale. Some spots are estimated to be less than 2 million years old. Ceres also shows evidence of cryovolcanism, volcanic activity involving icy material. A structure called Ahuna Mons resembles an extruded ice dome. This formation is about 4 kilometers high and lacks many impact craters, suggesting a young age. The presence of such structures indicates that Ceres is capable of transporting material from its interior to the surface. Cryovolcanism on Ceres is one of the clearest examples outside Enceladus. From an astronomical standpoint, Ceres serves as a natural laboratory for understanding intermediate bodies between asteroids and planets. Its density and internal structure offer clues about the formation of the solar system. It appears to have retained a significant amount of volatiles despite its relative proximity to the Sun. This factor is crucial for evaluating water distribution in the early stages of planetary evolution. The presence of water and salts makes Ceres a viable candidate for future exploration with practical purposes. Water extraction could be used to generate fuel via electrolysis, producing hydrogen and oxygen. This would allow spacecraft or crewed missions to refuel during long journeys. Additionally, using local resources reduces reliance on Earth-based launches. The idea of Ceres as a logistical support station is under evaluation by space agencies. Chemically, aliphatic organic compounds have been detected on Ceres's surface. These compounds are simple precursors to more complex molecules. Their origin may be internal through hydrothermal processes or external from comet impacts. The combined presence of water, salts, and organics places Ceres in the spotlight of astrobiology, although there is no direct evidence of habitability. Still, the environment is relevant for experiments and simulations. Ceres also contributes to understanding the transition between dry bodies and volatile-rich ones. Unlike Vesta, another large asteroid, Ceres exhibits a spectrum dominated by hydrated minerals. This suggests a distinct evolutionary history with possible internal differentiation. Comparative analyses with other belt objects helps map the initial conditions of the solar system. These comparisons are fundamental to planetary science. Future missions to Ceres are expected to focus on drilling through the crust to collect direct samples. This will require excavation technologies suitable for low-gravity, low-temperature environments. Isotopic analysis of the salts could reveal the origin of the water. Additionally, seismic sensors could detect internal activity. Such studies would help confirm the presence of active cryovolcanism and map the structure of the subsurface ocean. Ceres's topography includes craters, plains, and domes marked by landslides. The surface reveals complex modification processes over time. This includes impacts, ice flows, and sublimation-driven erosion. The dynamics of a frozen crust under moderate internal pressure is an active area of research. This behavior is comparable to other icy worlds and provides useful data for thermal modeling. Based on current observations, Ceres stands out as one of the most promising bodies for future operations in the inner solar system. Its combination of water, chemical compounds, and strategic location offers multiple scientific and operational possibilities. Continued investigations are needed to fully understand its geology, structure, and potential for use as a space resource. Comet 67P Churyumov-Gerasimenko contains ingredients for life, may have delivered organic compounds to Earth. Comet 67P Churyumov-Gerasimenko is a Jupiter family object with an orbital period of about 6.4 years around the Sun. It has an irregular shape with two connected lobes resembling a rubber duck. It measures approximately 4.3 by 4.1 kilometers. The surface is covered with dark, porous dust. Its study was revolutionized by the European Space Agency's Rosetta mission. Rosetta was the first spacecraft to orbit and accompany a comet for an extended period. It arrived at 67P in 2014 and deployed the Philae lander, which touched down on the surface. Despite technical difficulties during landing, Philae managed to transmit important data. Throughout the mission, Rosetta mapped the comet's topography, composition, and activity with high precision. These data transformed our understanding of active comets. 67P's surface features cliffs, pits, depressions, and flows of granular material. As the comet approaches perihelion, solar heat warms the nucleus, causing ice to sublime. This creates jets of gas and dust that escape at high speeds. The flows originate from surface fissures or cavities. The comet's activity varies with its orbital position, peaking at perihelion. One of the mission's main goals was to investigate the chemical composition of the nucleus. Various organic compounds were detected, including formaldehyde, methanol, hydrogen cyanide, and glycine, a simple amino acid. The presence of these materials supports the hypothesis that comets may have contributed organic molecules to early Earth. This delivery likely occurred during the late heavy bombardment. The COSAC spectrometer aboard Philae detected glycine and other compounds. Phosphorus was also confirmed, an element essential to life as we know it. These results suggest that comets are not merely icy, dusty blocks, but complex reservoirs of prebiotic molecules. They may have acted as chemical vectors in the evolution of Earth's system. Beyond organic chemistry, Rosetta studied the isotopic ratio of deuterium in the comet's water. The value found was 3 times higher than that of Earth's ocean water. This indicates that comets like 67P were not the primary source of Earth's water. However, their chemical contribution, in terms of complex molecules, remains relevant. The delivery of organic matter does not depend on isotopic compatibility of water. The comet's internal structure is porous with low density, about 0.5 grams per centimeter cubed. This suggests it is made of loose aggregates of ice and dust with many empty spaces. Its low cohesion explains the intense activity as it nears the Sun. It also means the nucleus is vulnerable to fragmentation. Structural stability studies help predict the behavior of other active comets. Rosetta's observations also showed that 67P's surface changes rapidly. Dust deposits are removed or redistributed following sublimation events. Some regions experienced collapses, indicating active erosion. This confirms that comets are dynamic and short-lived bodies on astronomical timescales. The evolution of their morphology depends heavily on cyclical thermal activity. The study of 67P also provided insights into the interaction between comets and the solar wind. The comet develops an induced magnetotail that extends millions of kilometers. The absence of an internal magnetic field revealed how ionized particles organize solely based on the cometary ionosphere. This helps us understand how comets affect the surrounding space environment. Spectral analysis of the comet revealed significant regional variations in surface composition. Some areas are richer in ice, while others concentrate dark organic material. This heterogeneity suggests a complex history of formation and alteration. The data are used to refine accretion models from the early solar system. They also indicate that comets may have formed through the merger of smaller objects. After the mission ended in 2016, the Rosetta spacecraft was intentionally crashed onto the comet's surface. This allowed for final low-altitude observations and reduced the risk of future collisions with satellites. The scientific legacy of the mission includes a vast data archive and new lines of research in prebiotic chemistry, comet dynamics, and nucleus evolution. 67P remains a landmark in the exploration of small bodies. The information obtained from 67P reinforces the importance of comets as natural archives of the solar system's earliest days. They preserve materials that have not undergone geological differentiation. Studying these bodies allows us to access conditions that existed over 4 billion years ago. This makes comets fundamental to reconstructing the chemical origin of Earth and the other planets. Sedna, extremely distant orbit, may indicate the presence of the mysterious Planet 9, which could reshape the entire dynamics of the solar system. Sedna is a trans-Neptunian object discovered in 2003 with an estimated diameter of approximately 1,000 kilometers. It belongs to a category of distant objects that orbit the Sun along highly elongated trajectories. Its distance from the Sun ranges from about 76 to 936 astronomical units. This places it well beyond the Kuiper belt, in a region known as the scattered disk or possibly the inner Oort cloud. Sedna never approaches the giant planets. Sedna's orbit is highly eccentric and takes approximately 11,400 years to complete. This extremely long orbital period makes real-time tracking and study difficult. Its orbit is also steeply inclined relative to the plane of the ecliptic. These features made Sedna an object of interest for models studying the gravitational boundaries of the solar system. It remains beyond the direct gravitational influence of the known planets. Sedna's orbit cannot be explained solely by the gravitational effects of Neptune or the Kuiper belt. This led to the hypothesis that its orbit was shaped by some unknown massive object. That idea forms one of the foundations of the proposed Planet 9, a hypothetical planet with a mass several times that of Earth, located hundreds of astronomical units away. Statistical studies of other objects with orbits similar to Sedna's have strengthened this theory. Some of these bodies share orbital alignments that do not appear to be random. This suggests that a common gravitational force may be acting upon them. Numerical modeling indicates that a distant, massive planet could maintain this orbital clustering. The direct search for this planet is underway using telescopes such as Subaru. Sedna's composition is not yet known with precision. Spectroscopic observations indicate a surface rich in complex organic compounds like tholins, along with traces of frozen methane and nitrogen. The object's reddish color is consistent with the presence of such materials. Because it is so far from the Sun, the sublimation of volatile ices is minimal. This preserves its surface from recent changes due to solar heating. Sedna is too small to retain a stable atmosphere, especially at its current orbital distance. However, it has been speculated that during its closest approach to the Sun, it might develop a temporary atmosphere. Thermal models suggest this would only occur in the innermost parts of its orbit. Even so, this possibility is of interest for studies of bodies with extreme seasonal activity. Because Sedna remains extremely distant for most of its orbit, detecting and monitoring it is challenging. Telescopes require long exposures to detect its faint light. Moreover, it moves slowly across the sky, requiring extended observation to confirm its path. Identifying more objects with similar orbits may help map this distant population. Sedna's importance lies in its potential to reveal the true boundaries of the solar system. It lies between the Kuiper belt and the outer Oort cloud. This position makes it a candidate for understanding how the Sun's gravitational field interacts with interstellar material. Models of solar system formation also explore whether Sedna could have been captured from another stellar system. There is also the possibility that Sedna is representative of an entire class of yet undiscovered objects. The difficulty in detecting such distant bodies implies that many may exist undetected. This changes mass estimates for the outskirts of the solar system. Modeling this population could shift our understanding of the Sun's long-term gravitational environment. Ongoing monitoring of Sedna provides data on its light curve, rotation, and possible surface variations. These data are used to estimate its shape, density, and composition. So far, it is unknown whether Sedna has natural satellites, but searches are ongoing. The presence of a moon would allow for more accurate determination of its mass. In orbital terms, Sedna is a puzzle. The inclination, eccentricity, and distance of its orbit deviate from the pattern of traditional minor bodies. This makes it critical for testing the limits of current dynamic models of the solar system. The coming decades are expected to yield new discoveries of similar objects, which will help confirm or refine existing theories. Sedna is not alone, but it is the most well-known of its extreme category. Studying it may be the key to confirming or dismissing the existence of yet unseen planets in the solar system. This makes Sedna a crucial piece in constructing the current model of the gravitational structure of our cosmic neighborhood. Chariklo, asteroid with rings, challenges theories on orbital stability, crucial for space engineering. Chariklo is a centaur, a type of celestial body with characteristics between asteroids and comets. It orbits the Sun between Saturn and Uranus, following an unstable and inclined trajectory. With a diameter of about 250 kilometers, it is the largest known centaur. Its surface is dark and low in reflectivity, suggesting a composition rich in organic compounds. What made it famous was the unexpected discovery of a ring system. In 2014, observations during a stellar occultation revealed two narrow rings around Chariklo. This was detected when the light of a background star was momentarily blocked by structures surrounding the asteroid, both before and after the main occultation. The rings are estimated to be 3 and 7 kilometers wide and are separated by about 9 kilometers. They lie at a distance of approximately 400 kilometers from Chariklo's center. The discovery was surprising because until then, rings had only been observed around giant planets. The presence of rings around such a small body challenged previous models of gravitational stability. In low-mass objects, particles were expected to either escape or fall inward quickly. In Chariklo's case, the rings appear to be stable over long periods, suggesting the existence of confinement mechanisms. One hypothesis for the ring stability involves the presence of small shepherd moons, which have not yet been directly observed. These moons would keep the ring particles confined to narrow orbits. Another possibility is that gravitational resonances among the particles themselves contribute to maintaining the structure. Numerical simulations are ongoing to better understand the orbital physics of this configuration. The origin of Chariklo's rings is also debated. One possibility is that they resulted from a collision that ejected material from the asteroid itself. Another hypothesis involves the tidal disruption of a small moon. The ring's composition, rich in frozen water, is consistent with Chariklo's surface material. This supports the idea that they were derived from the primary body. The stability of the rings provides valuable data for space engineering. Understanding how particles remain in stable orbits around small bodies can influence the design of artificial satellites. This knowledge also applies to asteroid mining missions. The physics governing Chariklo's rings offers real-world models for orbital simulation testing in microgravity environments. Moreover, the discovery inspired new observations of other centaurs. In 2017, signs of rings were found around Chiron, another body in the same class. This suggests that ring systems may be more common than previously thought. If confirmed, it would require revising models of material aggregation and retention in small bodies. This expands the field of small system dynamics. The study of Chariklo's rings may also shed light on early stages of planetary formation. The rings are simplified analogs of protoplanetary disks. Particle interactions, collisions, and clumping occur on a smaller scale but follow similar physical principles. This provides an accessible opportunity to observe processes that occur on stellar scales. Ongoing observations of stellar occultations by Chariklo are being coordinated to monitor changes in its rings. These observations could reveal variations in density, width, or shape. Over time, they will help determine whether the rings are dissipating or maintaining stability. Small variations may also hint at the presence of undiscovered moons. Instruments like the Very Large Telescope and the James Webb Space Telescope are candidates for more precise spectral analyses of the rings. Gathering data across different wavelengths may confirm their detailed composition. This would allow comparisons with planetary rings and with the surfaces of other centaurs. Full characterization is still underway. Chariklo also serves as a methodological reminder. Its discovery was only possible through coordinated observations from multiple locations on Earth. This highlights the importance of occultation techniques in studying small and distant objects. Applying this method in future campaigns may reveal more rings around little-studied bodies. The study of Chariklo represents a major leap in understanding small bodies with unexpected features. It demonstrates that complex dynamic structures can exist in low-gravity environments. This broadens the scope of orbital systems research and helps refine the limits of stability for particles orbiting asteroids and other small objects. Triton is Neptune's largest moon, with a diameter of approximately 2,710 kilometers. Unlike most large moons in the solar system, it has a retrograde orbit. It revolves around Neptune in the opposite direction of the planet's rotation. This unusual trait suggests that Triton did not form alongside Neptune. It is believed to have been gravitationally captured, likely as a Kuiper belt object. This capture left lasting dynamical effects. Triton's retrograde orbit is inclined and nearly circular, likely the result of a stabilization process following its capture. During this phase, interactions with other moons may have caused collisions or ejections. Triton eventually stabilized, but tidal friction between the Moon and Neptune continues. This interaction is gradually decreasing Triton's orbital altitude. In a few billion years, it may cross Neptune's Roche limit and fragment. If this scenario occurs, Triton could break apart and form a ring system around Neptune. Such an event would resemble the process believed to have created Saturn's rings, though with different materials. Dynamic models simulate the fragmentation of large moons in decaying orbits. The resulting system would depend on the moon's internal composition and its distance from the planet at the moment of disruption. Triton's composition is mixed, with roughly 2/3 rock and 1/3 ice. Its average density is 2.06 grams per cubic centimeter, indicating a differentiated interior. There is evidence of cryovolcanic activity on its surface, with frozen nitrogen and methane deposits. This suggests enough internal heat exists to allow movement of volatile liquids. The heat may come from radioactive decay and residual tidal forces. Triton's surface displays diverse terrains, including frozen plains, polar caps, and unique geological features. One highlight is the nitrogen geysers observed by Voyager 2 in 1989. These jets reach up to 8 kilometers in height and carry dark material across vast distances. The activity likely results from subsurface nitrogen sublimating, building pressure until it's suddenly released. In addition to geysers, Triton has polygonal terrain features that cover large areas. These are thought to result from convective processes in the surface ice. This type of structure resembles those seen in Earth's ice sheets, though it occurs at much lower temperatures. Such surface activity reinforces the idea that Triton is not geologically inert. Triton has a tenuous atmosphere composed primarily of nitrogen, with traces of methane. This atmosphere is seasonal, becoming denser as Triton approaches the Sun. Surface pressure is extremely low, around 14 microbars. Nevertheless, this thin layer enables haze formation and contributes to plume and jet dynamics. Triton is one of the few solar system bodies with documented atmospheric activity. Interest in Triton has increased with the rise of studies on subsurface oceans. It is believed that a liquid water ocean mixed with ammonia may lie beneath its icy crust. Indirect detection could be achieved through gravitational and magnetic studies. A liquid interior would heighten astrobiological interest, especially in comparison with moons like Europa or Enceladus. Triton orbits Neptune at about 354,000 kilometers and completes one orbit every 5.9 days. Its rotation is synchronous, meaning the same side always faces Neptune, a typical configuration for large moons. Orbital stability is aided by the absence of other massive nearby moons. This contributes to the maintenance of its retrograde orbit and continued tidal energy dissipation. Voyager 2 remains the only mission to have directly observed Triton. Most available data come from its 1989 flyby. New missions, such as NASA's proposed Trident, aim to revisit the Moon with modern instruments. The goal is to investigate its geology, atmosphere, and potential internal ocean. Triton's unique conditions make it a natural laboratory for extreme processes. Triton also holds significance for gravitational capture studies. Its presence around Neptune is direct evidence that giant planets can incorporate Kuiper belt objects. This mechanism has implications for planetary system formation in general. Triton's orbital dynamics offer a practical example of events that could occur in exoplanet systems with multiple bodies. Combining a retrograde orbit, cryogenic activity, and oceanic potential, Triton is one of the most complex moons in the solar system. In the long term, its inward spiral toward Neptune is inevitable. The outcome of this process is still under study, but it represents a large-scale gravitational event with the potential to reshape the host planet's environment. Arrokoth, formerly known as Ultima Thule, is a Kuiper belt object located about 6.6 billion kilometers from Earth. It was visited by NASA's New Horizons spacecraft on January 1, 2019, following its flyby of Pluto. Measuring approximately 36 kilometers in length, Arrokoth is composed of two connected lobes. Its shape resembles a flattened snowman, a structure known as a contact binary. Arrokoth's surface is relatively smooth, with few identified craters. This suggests it has remained nearly unaltered since its formation. The low-energy environment of the distant Kuiper belt allows bodies like Arrokoth to survive for billions of years. Its preservation provides a direct window into the early conditions of the solar system's formation. It stands as one of the most primitive objects ever observed up close. Arrokoth's composition includes methanol ice, ammonia, and complex organic compounds called tholins. These materials form through the exposure of volatile compounds to ultraviolet radiation and cosmic rays. Tholins are responsible for the reddish color observed on the surface. The presence of these compounds indicates that chemical processes can occur even at extremely low temperatures. Observations from New Horizons show Arrokoth has very low density, below 0.5 grams per centimeter cubed. This suggests it is highly porous, made of loosely bound aggregates. This structure supports the hypothesis that its two lobes merged slowly, avoiding a violent collision. The low-speed fusion preserved its current shape, consistent with gentle accretion models in the protoplanetary disk. Studying Arrokoth's shape and internal structure provide evidence for how planetesimals formed. Traditional theory suggested violent collisions between small bodies. Arrokoth, however, supports the model of local gravitational collapse of dust clouds. In this scenario, matter accumulates slowly and orderly. The result is porous, fragile bodies like this one. Spectral analysis of Arrokoth revealed compositional uniformity between the two lobes. This suggests both lobes formed in the same region of the early solar disk. The chemical similarity reinforces the idea of local formation and co-evolution. There is no evidence of internal differentiation or significant thermal activity. This sets Arrokoth apart from larger bodies that experienced internal heating. Arrokoth rotates slowly, with an estimated period of about 15.9 hours. The gradual illumination of its surface during the flyby allowed for detailed mapping of shadows and elevations. No faults or domes were identified. The absence of tectonic activity is expected for such a small and cold body. The stable topography aids in modeling primordial surfaces. The object shows no atmosphere or signs of volatile activity. This makes it an example of an inactive body in thermal equilibrium with the Kuiper Belt environment. Solar radiation is extremely weak in this region, limiting the sublimation of volatile materials. The environmental stability helps preserve ancient chemical compositions virtually unchanged since formation. Arrokoth was selected as a target by New Horizons due to its orbital accessibility and unusual characteristics. The mission expanded our knowledge of distant objects beyond Pluto. Before this, no spacecraft had closely observed such a primitive contact binary. It opened a new frontier for studying low-energy collision objects. New Horizons continues to transmit stored data from the flyby, enabling increasingly detailed analyses. These include multispectral images, thermal readings, and particle field data. This information is critical for comparing Arrokoth to other Kuiper Belt objects and refining models of outer solar system evolution. Arrokoth also serves as a reference point for identifying similar objects. Future missions may include comparable targets for comparative study. Identifying morphological and spectral patterns in new bodies will help test the generalizability of proposed models. This effort will be supported by advances in telescopes like the LSST and JWST. The study of Arrokoth confirms that primitive Kuiper Belt objects preserve essential information about planetary formation. Its detailed analysis complements data from other missions like Rosetta and Dawn. By combining shape, composition, and structure, Arrokoth has become a key case for understanding the earliest stages of the solar system. Haumea, egg-shaped dwarf planet with ultra-fast rotation and rings, a distorted gem floating in space. Haumea is a dwarf planet located in the Kuiper Belt, orbiting beyond Neptune. It was officially recognized by the International Astronomical Union in 2008. Measuring about 2,000 kilometers along its longest axis, Haumea has a markedly elongated ellipsoidal shape. This unusual geometry is directly linked to its extremely rapid rotation. The object completes one rotation every 3.9 hours, one of the shortest periods among large bodies in the solar system. This rapid spin generates significant centrifugal force, distorting Haumea and preventing it from becoming spherical. Its average density is estimated to be around 2.6 grams per cubic centimeter, suggesting a predominantly rocky interior. A thin outer layer of water ice covers part of the surface, as revealed by spectral observations. The distorted shape complicates the calculation of its mass and volume. Models are refined using variations in brightness over time. In addition to its unique form, Haumea hosts a ring system, confirmed in 2017 via stellar occultation. The ring is approximately 70 kilometers wide and orbits about 2,300 kilometers from Haumea's center. It is the first ring ever discovered around a trans-Neptunian object. The ring's origin remains uncertain, but may be linked to a collision or ejection of surface material. The structure appears stable, with particles following a well-defined orbit. Detection of the ring was made possible through a synchronized network of telescopes observing Haumea passing in front of a distant star. Subtle dips in brightness before and after the main occultation revealed the presence of orbiting material. Analysis of the light curve helped estimate the ring's width, opacity, and orbital distance. The structure is aligned with Haumea's equator, suggesting a connection to its rotation. Haumea also has two natural moons, Namaka and Hi'iaka. The larger, Hi'iaka, is about 310 kilometers in diameter and orbits roughly 50,000 kilometers away. The smaller Namaka measures about 170 kilometers. The orbits of these moons help estimate the total mass of the Haumea system. Both moons are believed to have originated from the same impact event that possibly formed the ring, as they share spectral features with the dwarf planet. Haumea's surface shows a strong spectral signature of crystalline water ice. This type of ice is unstable over long periods in the Kuiper belt, indicating recent surface renewal. The most accepted explanation is that collisions or cryogenic activity exposed fresh layers. Another possibility is that secondary impacts ejected and redistributed material, keeping the surface relatively clean. Haumea's fast rotation greatly influences its light curve. As the planet spins, the visible surface area changes dramatically, causing noticeable brightness fluctuations from Earth. These variations were among the first clues to its elongated shape. Light curve analysis is critical for small, distant bodies where direct imaging is not feasible. This method helps determine not just shape, but also surface properties. The Haumea system may represent the exposed core of a once larger body that lost part of its icy crust. This hypothesis explains its high density and rock-rich composition compared to similar Kuiper belt objects. Numerical models simulate catastrophic collisions capable of removing the outer ice layer. The group of objects with orbits similar to Haumea's further supports this idea, possibly representing fragments from the same impact. Haumea travels around the Sun in an eccentric orbit, completing one revolution every 284 Earth years. Its average distance is about 43 astronomical units. Its orbital plane is tilted roughly 28 degrees from the ecliptic, typical for Kuiper belt objects with active dynamical histories. Haumea's orbital stability is maintained through weak resonances with Neptune. Haumea's physical characteristics challenge traditional classifications. Its density, shape, rings, and moon system make it one of the most complex objects in the Kuiper belt. This makes it an excellent subject for studies of icy body formation and evolution. Its rotational dynamics, in particular, offer unique data for physical modeling. Haumea serves as a counterpoint to spherical objects like Pluto or Eris. So far, no mission has been sent specifically to Haumea. Its great distance and small size make direct exploration difficult. However, future missions to trans-Neptunian objects may include planned flybys using gravity-assist maneuvers. Advances in electric propulsion and trajectory planning could make such missions feasible. Growing scientific interest reinforces Haumea's value as a priority target. The study of Haumea continues to rely on both ground and space-based telescopes. Photometric, spectroscopic, and occultation observations remain the primary tools. Combined analysis of its orbital, geophysical, and structural parameters supports models of collision, accretion, and rotational evolution. Haumea remains a striking case of small-scale complexity in the outer solar system. Iapetus is the third largest moon of Saturn, measuring about 1,470 kilometers in diameter. Discovered by Giovanni Cassini in 1671, this moon is best known for its dramatic visual contrast. One hemisphere is as bright as snow, while the other is as dark as coal. This stark albedo difference is so extreme that Cassini could only observe the moon during part of its orbit, a puzzle that remained unsolved for centuries. The dark hemisphere is known as Cassini Regio, while the bright side is called Roncevaux Terra. The cause of this dual-tone appearance remains under investigation. One hypothesis suggests that dark particles from moons like Phoebe are deposited on Iapetus by micrometeoroid impacts. Another theory proposes that the dark side absorbs more sunlight, triggering ice sublimation that migrates to the cooler bright side, a feedback loop that amplifies the contrast. Both processes may work together to sustain the effect. The bright side of Iapetus reflects up to 60% of incoming sunlight, composed mostly of relatively pure water ice. In contrast, the dark side reflects less than 10%, producing significant thermal differences. These thermal gradients likely drive the redistribution of surface ice. Most of what we know comes from the Cassini spacecraft, which flew by Iapetus in 2004 and 2007, capturing high-resolution images that reveal detailed albedo patterns. Another astonishing feature is the Equatorial Ridge, a mountain chain stretching over 1,300 kilometers along the Moon's equator, with peaks reaching up to 20 kilometers high. This ridge ranks among the tallest in the solar system in proportion to Iapetus's size. Its origin is unknown. Hypotheses range from remnants of a primordial ring that collapsed onto the equator to ancient cryovolcanic activity. There is no definitive explanation yet. Iapetus is tidally locked, meaning it always shows the same face to Saturn. It has an unusually long orbital period of 79 Earth days, especially for a moon its size. This slow orbit may have amplified the thermal asymmetry that fuels the surface contrast. Its orbital distance from Saturn is about 3.5 million kilometers, making it one of the more distant major moons of the planet. With an average density of just 1.08 grams per centimeter cubed, Iapetus is composed mostly of water ice with a small amount of rock. This low density makes the moon structurally weak and contributes to its slightly flattened shape, especially near the poles. Its incomplete hydrostatic equilibrium suggests a limited internal thermal history. The equatorial ridge may be a product of mass redistribution rather than deep internal activity. The surface is heavily cratered, showing little sign of recent geological renewal. Most of the terrain has remained unchanged for billions of years. Some evidence of landslides along the equatorial ridge hints at localized movement, but there's no indication of tectonic or volcanic processes in recent times. These observations support the idea that Iapetus has been geologically inactive for most of its history. Thermal evolution models suggest that Iapetus never retained enough internal heat for sustained cryovolcanism. The absence of tectonic fractures supports this cold and rigid state. The Moon likely cooled quickly after formation, halting internal differentiation. This would explain its low density and the lack of internal activity, making Iapetus a well-preserved remnant of ancient solar system conditions. The Phoebe dust hypothesis posits that particles from Saturn's outer rings gradually migrate inward and collide with Iapetus, particularly on its leading hemisphere. Once settled, this dark material absorbs more heat, which enhances ice sublimation in that region. This creates a self-reinforcing thermal feedback mechanism, where the dark side becomes darker and the bright side becomes brighter over time. Photometric and spectroscopic studies reveal that the dark material is rich in organic compounds such as hydrocarbons. These are consistent with materials found throughout the outer solar system. The exact source remains uncertain. It could result from continuous impacts or steady deposition from Phoebe's debris. This composition provides key data for understanding moon-ring interactions in icy environments. Despite its unique features, Iapetus is not currently a priority for future space missions. Its distant orbit and lack of active geology lower its appeal compared to other moons like Enceladus or Titan. However, the equatorial ridge and hemispheric contrast remain open mysteries. Continued remote observations can still yield valuable insights into comparative planetary science. Iapetus stands as a rare example of extreme hemispheric asymmetry and unique topographic structure. Studying it deepens our understanding of thermal processes, exogenous deposition, and shape stability in icy bodies. Among Saturn's many moons, Iapetus is a visual and scientific outlier, a frozen paradox that continues to challenge our models of planetary evolution. Pan, a ravioli-shaped mini-moon floating inside Saturn's rings. Pan is one of Saturn's smallest moons, with a mean diameter of about 28 kilometers. It orbits within the Encke Gap, a 325-kilometer-wide division in Saturn's A-ring. This small moon acts as a shepherd, maintaining the gap through gravitational interactions with surrounding ring particles. Pan's orbit lies at approximately 134,000 kilometers from Saturn's center. It was first discovered in 1990 through analysis of Voyager 2 images. What makes Pan especially remarkable is its unusual shape. It resembles a ravioli or flying saucer, with a flattened central body and a prominent equatorial ridge. This shape is caused by the accumulation of ring material pulled in by Pan's gravity. As particles collide with the moon's equator, they gradually build up a ridge-like structure. The result is a moon with geometry unlike any other known natural satellite. Pan's low gravity allows even small impacts to influence its structure significantly. The equatorial ridge extends around its entire circumference and rises several kilometers above the surface. Its unusual morphology was confirmed in detail by the Cassini spacecraft in 2017. High-resolution images revealed fine ridges, grooves, and a smooth outer rim. These features support the idea that Pan is still interacting with the ring particles today. Pan's orbit is nearly circular and lies very close to Saturn's equatorial plane. It completes one revolution around the planet roughly every 13.8 hours. Its gravitational field clears a path in the A-ring and also induces wave patterns along the edges of the Encke Gap. These waves help scientists model the internal structure and dynamics of Saturn's rings. Pan's mass is estimated at around 4.95 times 10 to the 15 kilograms. The moon's surface appears relatively smooth, lacking the high crater density typical of older moons. This suggests ongoing surface modification, likely due to continual bombardment by ring particles. Its reflectivity, albedo, is also similar to that of the surrounding rings, implying a shared origin or constant material exchange. No atmosphere or magnetofield has been detected. Pan's environment is dominated by Saturn's powerful magnetosphere. Pan is not alone in this class of unusual inner moons. Others, like Atlas and Daphnis, also orbit within the ring system and show signs of equatorial ridges. However, Pan's structure is the most developed and symmetric among them. Studying these moons provides insight into ring-moon interactions in low-gravity environments. It also reveals how small bodies can evolve through passive accumulation rather than active geology. Pan's formation is thought to have occurred after Saturn's rings were already in place. The moon likely accreted from material near the ring plane, collecting particles along the way. Its current role as a shepherd moon helps maintain the sharp boundaries of the Encke Gap. The balance between gravitational influence and particle flow is a dynamic system. It provides a real-world laboratory for studying disk-satellite interactions. The shape and dynamics of Pan also inform theories about how moons form in debris disks around young planets. The process seen in Saturn's rings may mirror larger-scale events in exoplanetary systems. In this context, Pan acts as a microcosm of planetary formation. The study of such structures can help refine models of accretion, migration, and disk clearing. These processes are critical to understanding early solar system development. Pan's proximity to Saturn exposes it to strong tidal forces. These forces may contribute to internal stress, though Pan's small size likely prevents significant heating. Still, over geologic timescales, tidal interactions can influence orbital evolution. The Moon's shape may also reflect long-term mechanical relaxation under competing forces. Observations suggest it has maintained stability despite ongoing surface alteration. Unlike larger moons, Pan lacks the gravitational energy to drive internal geological activity. There are no signs of tectonics, volcanism, or subsurface oceans. Its evolutionary path is dominated by external interactions and passive accumulation. This distinguishes it from geologically active bodies like Enceladus or Io. Yet Pan remains scientifically valuable due to its unique position and morphology. The Cassini mission's close-up images of Pan were essential in identifying its ridge structure. These observations allowed scientists to create detailed 3D models of the Moon's shape. By analyzing light curves, surface features, and particle dynamics, researchers have built simulations of ring-moon interactions. Such models enhance understanding of small-scale gravitational systems. Future missions may revisit Pan for even closer study. Pan serves as a key case study in the physics of ring-moon systems. Its unusual shape and active interaction with Saturn's rings challenge traditional definitions of moon structure. Continued monitoring and modeling of Pan's behavior help refine our understanding of disk dynamics, accretion physics, and the long-term evolution of small celestial bodies. Hyperion, a sponge-like body with completely chaotic rotation. Hyperion is a mid-sized moon of Saturn with a mean diameter of about 270 kilometers. It is irregularly shaped, resembling a flattened ellipsoid rather than a sphere. This irregularity, combined with a low density of around 0.55 grams per cubic centimeter, makes Hyperion one of the least dense solid bodies known. Its surface is covered with deep, sharp-edged craters. These features give it a porous, sponge-like appearance in images. The texture of Hyperion is unusual among moons. Its surface porosity is estimated to exceed 40%, meaning much of the volume is empty space. This low density suggests the moon is composed mostly of ice with some rock and is loosely packed. The lack of compaction indicates it has not undergone significant thermal evolution. The surface retains features from billions of years ago. One of the most distinctive aspects of Hyperion is its chaotic rotation. Unlike most large moons, Hyperion does not rotate predictably around a stable axis. Instead, its spin axis changes randomly due to gravitational interactions with Titan, Saturn's largest moon. This phenomenon is called chaotic rotation and was confirmed by analysis of Voyager and Cassini data. As a result, the orientation of Hyperion's surface changes constantly. Hyperion's orbital period is about 21.3 days, but its rotation period varies unpredictably. It can tumble in different directions with no fixed period or axis. This makes it extremely difficult to model its rotational state over time. The cause of this instability lies in its irregular shape and Titan's resonant gravitational influence. Hyperion is one of the only known bodies in the solar system with confirmed chaotic spin. The Moon orbits Saturn at a distance of approximately 1.48 million kilometers. It shares a 4-3 orbital resonance with Titan, meaning it completes 4 orbits for every 3 of Titan's. This near resonance contributes to the rotational chaos. Small changes in orbital parameters can lead to large changes in spin dynamics. Hyperion's motion is a real-world example of deterministic chaos in celestial mechanics. Cassini's close flybys provided detailed images and data on Hyperion's surface and structure. The spacecraft detected an abundance of carbon-based compounds, including possible tholins. These reddish organic materials form through ultraviolet irradiation of simpler molecules. The distribution of such compounds on Hyperion adds to evidence of widespread organics in the outer solar system. It also aids comparisons with other icy bodies. The cratered surface of Hyperion is distinctively jagged and sharp-edged. This indicates that the Moon has not experienced significant erosion or relaxation. The low gravity prevents ejecta from escaping, causing material to settle back into the craters. Additionally, its high porosity dampens impact shock waves, preserving sharp features. Craters tend to be closely spaced and uniform in depth, unlike smoother surfaces on other moons. The interior of Hyperion is believed to be homogeneous, with no evidence of differentiation. The lack of internal heating implies it never developed a layered structure. Its low density precludes the existence of a liquid core or subsurface ocean. The Moon is essentially a frozen rubble pile held together by self-gravity. This makes it valuable for understanding small body formation and internal structure. Hyperion does not exhibit any signs of current geological activity. There are no tectonic features, cryovolcanic flows, or active vents. The surface appears static and ancient, shaped almost entirely by impact cratering. Its chaotic rotation also prevents localized heating or stress accumulation. This inert behavior is consistent with its size, composition, and thermal history. Its orbit is moderately eccentric, adding to the complexity of its motion. Although tidal interactions with Saturn exist, they are insufficient to stabilize the spin. Over time, Hyperion may evolve further, but its chaotic nature likely persists for millions of years. The unpredictability of its rotation is of interest for theoretical studies in nonlinear dynamics and orbital mechanics. The study of Hyperion contributes to understanding the diversity of satellite behaviors in the Saturnian system. It provides a natural case study of how shape, mass distribution, and orbital context can lead to rotational chaos. These insights are applicable to exoplanet systems and asteroid belts. They demonstrate how irregular geometry can result in long-term dynamical instability. Hyperion remains one of the most unusual moons in the solar system due to its shape, porosity, and unpredictable spin. It challenges assumptions about rotational behavior in celestial bodies. Continued analysis of Cassini data and possible future missions may refine our understanding of this chaotic and sponge-like moon. Miranda is a moon stitched together from incompatible pieces, features 20-kilometer cliffs and fractured terrain. Miranda is one of Uranus's major moons with a diameter of about 470 kilometers. Despite its small size, Miranda exhibits some of the most extreme and puzzling surface features in the solar system. It was discovered in 1948 by Gerard Kuiper and later studied in detail by Voyager 2 in 1986. What surprised scientists was the moon's chaotic landscape. Vast cliffs, canyons, and mixed terrains suggest a violent geologic history. One of Miranda's most notable features is Verona Rupes, a massive cliff that rises up to 20 kilometers. This is the tallest known cliff in the solar system. The origin of such a steep drop is unclear, but it likely results from tectonic or impact-related forces. If material were to fall from its edge, the free fall would last over 10 minutes. The presence of such formations on a small moon is unusual. The surface of Miranda is divided into regions with drastically different geologies. Some areas are heavily cratered and ancient, while others show grooved terrain and bright ridges. These younger regions are known as corona, with names like Arden, Elsinore, and Inverness. They consist of intersecting ridges and troughs that appear to overlay older surfaces. The boundaries between terrains are abrupt and poorly understood. The patchwork appearance of Miranda has led to theories that it was once shattered and reassembled. In this scenario, a massive impact broke the Moon apart, and gravity later pulled the fragments back together. This would explain the disjointed alignment of surface features. However, this remains a hypothesis, and alternative theories include resurfacing driven by internal activity. Both ideas attempt to explain Miranda's conflicting terrains. Voyager 2 images suggest tectonic activity, with clear signs of extensional faults and uplifted blocks. These features indicate that Miranda may have experienced internal heating at some point. The source of this heating is debated, but tidal forces from Uranus could be responsible. If so, Miranda's orbit must have been more eccentric in the past. This would have generated tidal friction and deformation. The Moon's density is about 1.2 grams per centimeter cubed, indicating a mixture of water ice and rock. Its low density suggests that it is not fully differentiated. That means it lacks distinct internal layers like a rocky core or icy mantle. Any thermal activity in its history would have been brief or limited in scope. Even so, such a small moon exhibiting tectonic restructuring is notable. The surface is also marked by complex canyon systems, with some extending hundreds of kilometers. These features resemble graben structures formed by crustal extension. The walls of these canyons are steep and layered, suggesting episodes of fracturing and collapse. No signs of cryovolcanism have been detected, but smoother plains may indicate past icy flows. These interpretations are constrained by limited imaging coverage. Miranda orbits Uranus at a distance of about 130,000 kilometers and completes one orbit in 1.4 Earth days. Its rotation is synchronous, always showing the same face to Uranus. It lies within the inner system of Uranian moons and interacts gravitationally with others like Umbriel and Ariel. These interactions may have influenced its past orbital eccentricity. Current tidal effects are weak, but historical models support a more active past. The Moon's surface temperature is extremely low, averaging around negative 187 degrees Celsius. At these temperatures, water ice behaves like rock. This allows the formation of steep cliffs and sharp fractures that would collapse on Earth. The preservation of these features suggests a stable surface with minimal erosion. Impact cratering is unevenly distributed, consistent with varying resurfacing ages. Due to the limited flyby by Voyager 2, only about 40% of Miranda's surface has been imaged in detail. Much of the remaining surface remains unexplored, which limits our understanding of global geological processes. Proposed future missions to Uranus could provide better imaging and compositional data. This would help confirm tectonic histories and clarify the origins of its unique terrains. Miranda does not possess an atmosphere, magnetic field, or any sign of ongoing activity. It is geologically inactive today, but retains a fossil record of dynamic processes. Its surface morphology provides valuable data for understanding tectonics in icy moons. The mix of terrains remains one of the clearest signs of violent and localized geological change in the outer solar system. The unusual combination of extreme topography, abrupt transitions, and structural complexity makes Miranda a key subject in comparative planetology. Despite its small size, it exemplifies how internal and external forces can produce dramatic surface evolution. Further investigation will depend on the development of dedicated Uranus system missions. Makemake, an icy dwarf planet with strange reflectivity and a possible intermittent atmosphere. Makemake is one of 5 officially recognized dwarf planets in the solar system and resides in the Kuiper Belt. It was discovered in 2005 and later named after a deity from the Rapa Nui mythology of Easter Island. With an estimated diameter of 1,430 kilometers, Makemake is slightly smaller than Pluto. It follows a moderately inclined and elliptical orbit that takes about 305 years to complete. It is one of the brightest known Kuiper Belt objects. Makemake's surface reflectivity is unusually high, with an albedo around 0.77. This suggests a surface coated in fresh, bright ices, mostly methane and possibly ethane. Spectroscopic studies have confirmed the presence of frozen methane as well as nitrogen and traces of other volatile compounds. The uniform brightness across its surface suggests recent resurfacing or atmospheric processes. However, no seasonal changes have yet been directly observed. Unlike Pluto, Makemake shows no clear signs of a stable atmosphere. In 2011, a stellar occultation revealed that it lacks a significant gaseous envelope. However, researchers proposed that Makemake may possess a temporary or patchy atmosphere. During parts of its orbit closer to the Sun, some of its surface ices may sublimate and form localized gas pockets. These would collapse again as the planet recedes into colder regions. Makemake's density is estimated at about 1.7 grams per cubic centimeter, indicating a composition of rock and ice. This value is similar to other large Kuiper Belt objects. Its internal structure may be differentiated, with a rocky core and icy mantle. However, no data currently confirms this division. Thermal models suggest past heating may have enabled partial internal restructuring. The dwarf planet has a single known moon, discovered in 2016 and named MK2. The moon is estimated to be about 160 kilometers in diameter. It orbits Makemake at a distance of roughly 21,000 kilometers. Observations of MK2 help refine mass estimates for the system. They also allow scientists to model Makemake's gravitational field and infer its internal composition. The presence of methane and nitrogen ices raise questions about Makemake's ability to retain volatiles. At its current distance from the Sun, these substances should be stable on the surface. However, sublimation could still occur at localized hotspots or during closer perihelion passes. The retention of volatiles suggests Makemake has enough mass and surface pressure to prevent immediate atmospheric loss. High-resolution thermal observations from instruments like Spitzer and Herschel have helped map surface temperatures. The data confirm extreme cold, with averages near -240 degrees Celsius. These conditions help preserve volatile ices over astronomical timescales. The reflective surface also minimizes heating from solar radiation. These thermal characteristics are typical for large trans-Neptunian objects. Makemake's brightness varies slightly over time, likely due to rotational modulation. It has a rotation period of roughly 7.7 hours, determined by monitoring light curves. These light variations help map surface heterogeneity. Small changes in albedo or topography may be present, though they remain unresolved at current resolution. No polar cap asymmetries have been detected. The surface coloration is moderately red, consistent with organic tholins produced by radiation. These complex molecules result from the photolysis of methane and nitrogen. Similar processes occur on Pluto and other outer solar system bodies. The spectral signature of Makemake supports the idea that radiation chemistry shapes its surface over time. The exact distribution of compounds remains uncertain. Makemake's orbit places it near the classical Kuiper Belt region, but its moderate eccentricity and inclination suggest a more dynamic history. It may have been perturbed by Neptune's migration or past collisions. These factors could explain the loss of any dense primordial atmosphere. The lack of current atmospheric pressure distinguishes it from Pluto and Triton. No spacecraft has yet visited Makemake. Observations rely entirely on Earth-based telescopes and space observatories. Future missions to the Kuiper Belt may target Makemake for flybys or orbital studies. Its high albedo and volatile-rich surface make it an ideal candidate for studying the diversity of icy dwarf planets. Mission feasibility depends on launch windows, propulsion, and long-term planning. Makemake remains one of the most intriguing bodies in the Kuiper Belt. Its reflective surface, suspected transient atmosphere, and single moon provide important comparative data. Together with Pluto and Eris, it contributes to building a clearer picture of the outer solar system's evolution and structure. Phoebe is a dark Saturnian moon, likely captured from the solar system's edge. Phoebe is one of Saturn's irregular outer moons, measuring about 213 kilometers in diameter. Unlike Saturn's large regular satellites, Phoebe has a retrograde and highly inclined orbit. It circles the planet at a distance of over 12 million kilometers, far beyond the main ring system. This trajectory, combined with its composition, suggests it may not have formed around Saturn. Instead, Phoebe is likely a captured object from the Kuiper Belt. Its surface is unusually dark, with an albedo of only 0.06, meaning it reflects just 6% of the light that hits it. This makes Phoebe one of the darkest known moons in the Saturnian system. Spectroscopic observations reveal a surface rich in carbon and dark organic compounds. Water ice has also been detected, along with possible signs of phyllosilicates and carbon dioxide. These materials are consistent with primitive outer solar system bodies. The Cassini spacecraft performed a close flyby of Phoebe in 2004, providing the first detailed images and data. These revealed a heavily cratered surface with varied topography. Some craters are more than 50 kilometers wide, indicating a history of violent impacts. One hemisphere appears slightly brighter due to exposed ice, possibly from subsurface layers. Phoebe's complex surface offers clues about its evolution and origin. Phoebe's shape is roughly spherical, but somewhat flattened, with no significant equatorial ridge or axial symmetry. Its density is about 1.6 grams per centimeter cubed, suggesting a mix of rock and ice. This density is higher than that of Saturn's inner icy moons, but lower than purely rocky asteroids. It supports the idea that Phoebe formed in a colder region of the solar system, where icy materials could accumulate. This aligns with Kuiper Belt origin hypotheses. Its retrograde orbit is highly eccentric and inclined by nearly 175 degrees relative to Saturn's equator. This orientation is incompatible with formation in Saturn's accretion disk. Most regular moons orbit in the same direction as their planet's rotation, on near-circular paths. Phoebe's orbital behavior is a strong indicator of gravitational capture. Models suggest it may have been pulled in during Saturn's early growth phase. Phoebe's interaction with Saturn's magnetosphere is minimal due to its distance. It also lacks any detectable atmosphere or magnetic field of its own. No current geological activity has been observed. Its surface remains static, shaped only by impacts and solar radiation. This inactive state is typical of small, distant moons without internal heating. Interestingly, Phoebe may be responsible for creating one of Saturn's largest ring structures. The Phoebe ring is a vast, diffuse cloud of dust extending from 6 to 12 million kilometers. It is invisible to optical telescopes, but detectable in the infrared. The particles are thought to originate from micrometeorite impacts on Phoebe's surface. These particles gradually spiral inward toward Saturn. This dust may explain the dark material observed on the leading hemispheres of Saturn's outer moons like Iapetus. Phoebe, acting as a source of debris, may have delivered carbon-rich compounds to other bodies. This transfer mechanism adds complexity to understanding surface compositions in the Saturnian system. It also highlights the role of distant moons in shaping planetary environments. Phoebe's orbit is not stable over extremely long timescales. Gravitational perturbations from the Sun and other moons cause gradual changes in its path. However, current models show it has been bound to Saturn for billions of years. Its continued presence supports the idea of early capture followed by long-term orbital evolution. These dynamics are relevant to understanding irregular satellite systems elsewhere. The flyby by Cassini remains the only close observation of Phoebe to date. It provided high-resolution images and direct measurements of surface properties. The data confirmed Phoebe's compositional similarity to Kuiper Belt objects and centaurs. This evidence helped place it in the broader context of solar system formation and migration. It bridges the gap between icy moons and trans-Neptunian objects. Phoebe lacks any moons or nearby companions. It occupies a relatively isolated orbital space, far from Saturn's denser satellite populations. This isolation limits mutual interactions and surface exchange processes. As a result, Phoebe serves as a preserved relic of early planetary formation, with minimal interference from neighboring bodies. Future missions to the outer solar system could revisit Phoebe or other irregular moons. Direct sampling or more detailed flybys could refine understanding of its origin, age, and surface chemistry. Phoebe remains an important target for comparative studies of captured satellites and primitive solar system materials. Themis, an asteroid that unexpectedly contains ice and organics, potential clue in Earth's water origin. Themis is a large main-belt asteroid with a diameter of about 200 kilometers. It resides in the outer region of the asteroid belt between 3.1 and 3.2 AU from the Sun. First discovered in 1853, Themis belongs to the Themis family of asteroids, which share similar orbital characteristics. It was long thought to be a typical rocky body. However, observations in the 21st century revealed unexpected surface features. In 2009, infrared spectroscopy detected water ice on Themis's surface. This was surprising because solar radiation should sublime surface ice over time at that distance. The presence of ice suggests either a stable subsurface reservoir or recent resurfacing events. Periodic exposure of fresh ice could result from impacts or thermal cracking. These processes allow surface renewal despite the asteroid's age. Alongside water ice, researchers also detected organic compounds on Themis. These include complex carbon-based molecules, such as tholins and polycyclic aromatic hydrocarbons. Their presence indicates that the building blocks of life may be more common than previously believed. It also shows that even main-belt asteroids can retain volatile and organic materials. This challenges earlier distinctions between asteroids and comets. The combination of ice and organics raises questions about the role of asteroids in delivering materials to Earth. Traditional models emphasize comets as the primary source of water and prebiotic molecules. However, Themis demonstrates that some asteroids may also have played a key role. Its orbital position suggests it could have intersected early Earth's path. Impacts from such bodies might have seeded our planet with water and carbon. The surface of Themis is moderately dark, with an albedo of about 0.07. This low reflectivity aligns with carbonaceous chondrite meteorites found on Earth. Its spectral type is classified as C-type, indicating a primitive and unaltered composition. The dark coloration is typical of ancient bodies that have undergone little thermal processing. It supports the view of Themis as a preserved solar system relic. Thermal models suggest that water ice on Themis should only be stable beneath a few meters of insulating dust. Its continued surface detection implies that internal or external processes replenish it. Sublimation may drive slow erosion or venting. Alternatively, small impacts may expose new patches of ice. These hypotheses remain under active investigation. Themis is part of a larger asteroid family resulting from a past collisional breakup. This means that other members of the Themis family may also contain ice and organics. Studies of related bodies like 24 Themis and 90 Antiope support this idea. If confirmed, this would expand the category of volatile-rich main belt asteroids. It would also offer broader insight into planetary delivery mechanisms. The presence of ice suggests that Themis may have formed farther from the Sun and migrated inward. Alternatively, the early solar system may have had a wider distribution of ices than currently modeled. This would change the understanding of snowlines and volatile boundaries in planetary formation zones. More data is needed to test these models. Unlike comets, Themis does not display a visible coma or tail. This indicates that any outgassing is extremely limited or occurs beneath detection thresholds. It blurs the line between comets and asteroids, supporting the concept of transitional objects. These bodies show that classification by activity alone may be insufficient. Composition and internal structure offer better distinctions. Themis's rotational period is about 8.4 hours, with minor variations in brightness during its spin. This suggests a relatively uniform surface with some localized variation. Photometric data supports the idea of surface heterogeneity. These variations could be tied to impact craters, ice patches, or darker organic deposits. Detailed mapping would require a close spacecraft mission. Themis is not currently targeted by any space missions. However, its unexpected properties make it a prime candidate for future exploration. A probe could investigate surface composition, internal structure, and ice dynamics. It would also provide direct comparison with cometary materials. Such missions could test theories of water delivery to early Earth. Themis has altered how scientists view the boundaries between asteroid types and their role in planetary evolution. Its mixture of ice, rock, and organics offers a model for studying early solar system chemistry. It challenges previous assumptions and expands the search for water-rich objects beyond traditional comet populations. Tempel 1, a comet that changed its appearance after spacecraft impact, shows unstable behavior. Tempel 1 is a periodic comet from the Jupiter family, discovered in 1867 by Wilhelm Tempel. It orbits the Sun every 5.5 years and has a semi-major axis of about 3.1 AU. The comet's nucleus is irregular in shape, approximately 7.6 kilometers long and 4.9 kilometers wide. It is composed of dust, rock, and volatile ices typical of primitive solar system material. Like most comets, it becomes active when approaching the Sun. In 2005, NASA's Deep Impact mission made history by deliberately colliding a probe with Tempel 1. The impactor struck the comet's surface at 10.2 kilometers per second, creating a visible plume of dust and debris. The goal was to expose subsurface material and analyze its composition. Observations from telescopes and the flyby spacecraft revealed details of the internal structure. It provided the first direct look beneath a comet's crust. The collision revealed that Tempel 1 has a porous and fragile surface. The material excavated was fine-grained, with lower density than expected. Spectral analysis indicated the presence of water ice, silicates, and organic molecules. These findings supported the idea that comets could have delivered prebiotic material to early Earth. These compounds include formaldehyde, methane, and carbon-based chains. While not unique to Tempel 1, their presence adds to the inventory of primitive molecules in comets. They provide clues about the chemical conditions of the early solar system. Comet Tempel 1 does not follow a perfectly stable path. Its orbit is affected by gravitational interactions with Jupiter and other planets. Over long timescales, its perihelion and inclination can shift. These perturbations influence how much solar energy it receives, altering its activity cycle. The comet's long-term stability remains subject to ongoing gravitational modeling. The nucleus's low density, estimated at 0.4 grams per centimeter cubed, indicates a high degree of porosity. This is typical for comets, which are composed of loosely packed icy grains and dust. Such structures are fragile and prone to fragmentation. This fragility explains why many comets break apart or disintegrate over time. Tempel 1 has so far survived multiple perihelion passages. Infrared observations during flybys detected heat anomalies and surface temperature gradients. These data help model the thermal conductivity and structure of cometary layers. Regions with higher dust cover tend to retain heat longer. Sublimation rates depend both on composition and insulation. Understanding these dynamics is key to predicting outgassing behavior. The discovery of organics on Tempel 1 supports the idea that comets could have delivered prebiotic material to early Earth. These compounds include formaldehyde, methane, and carbon-based chains. While not unique to Tempel 1, their presence adds to the inventory of primitive molecules in comets. They provide clues about the chemical conditions of the early solar system. Tempel 1 remains an important target for comet science due to its documented changes and direct impact experiment. Future missions may revisit it or similar bodies to build on past findings. It serves as a benchmark for understanding cometary evolution, structure, and composition. Continued observation is essential to monitor its long-term changes. Nereid is a Neptune moon with a wildly eccentric, nearly chaotic orbit. Nereid is the third largest moon of Neptune and one of the most distant regular satellites in the solar system. It was discovered in 1949 by Gerard Kuiper. Nereid orbits Neptune at a distance ranging from about 1.4 million to over 9.6 million kilometers. This highly elliptical orbit is one of the most eccentric known for a moon. Its behavior has puzzled astronomers for decades. Nereid's orbit has an eccentricity of about 0.75, which causes dramatic changes in distance during each revolution. Its orbital period is roughly 360 Earth days. This variability in distance leads to significant changes in its apparent brightness. Ground-based observations have confirmed these fluctuations. The cause of the eccentricity remains a subject of study. One theory suggests that Nereid was once a regular moon of Neptune, but had its orbit disrupted. The likely culprit is Triton, another Neptunian moon, captured later by Neptune's gravity. Triton's arrival would have destabilized the original satellite system. Nereid may be one of the survivors of that chaotic rearrangement. Its current orbit supports this captured disruption scenario. Nereid's shape is not precisely known due to limited imaging data. It is estimated to be roughly spherical, with a diameter around 340 kilometers. Voyager 2 provided low-resolution images during its 1989 Neptune flyby. The images were insufficient to resolve surface features or rotational details. More precise measurements await future missions or advanced telescopes. Its surface reflectivity is moderately high, with an albedo of about 0.24. This suggests a surface composed of water ice and silicates. No detailed compositional data exists, but its spectrum aligns with other outer solar system objects. Given its distance from Neptune and lack of tidal heating, surface evolution is likely driven by impacts and space weathering. No atmosphere or geological activity has been detected. Due to its long and eccentric orbit, Nereid experiences widely varying gravitational and radiation environments. At peri-Neptune, it passes through stronger magnetic and particle fields. At apo-Neptune, it drifts in a more isolated region. This variation could affect its surface temperature and charge interactions. However, these effects remain poorly constrained. Rotational characteristics of Nereid are still uncertain. Some studies suggest a slow or even chaotic spin. Its brightness variations hint at complex rotation, possibly influenced by past gravitational interactions. Nereid may be in a non-principal axis rotation, also known as tumbling. This would make it dynamically unstable compared to synchronous moons. No moons or ring structures have been found around Nereid. Its isolation limits interactions with other bodies in the Neptunian system. This makes it a relatively pristine object, potentially preserving ancient materials. Its orbital path also suggests it has avoided major collisions. This relative stability contrasts with its orbital irregularity. Triton, the dominant moon of Neptune, may have played a decisive role in shaping Nereid's trajectory. Triton orbits in the opposite direction of Neptune's rotation and is believed to be a captured Kuiper belt object. Its capture likely disrupted the orbits of other moons. Nereid may be one of the few remnants of Neptune's original satellite system. Current data on Nereid is sparse. Only Voyager 2 has observed it directly and at a great distance. Most of what is known comes from photometric monitoring and orbital analysis. Nereid remains a candidate for future exploration, especially in missions targeting Neptune or the outer solar system. Close-up data would clarify its rotation, geology, and history. Due to its extreme orbit and possible connection to planetary migration, Nereid is scientifically valuable. Its existence offers clues about how giant planet satellite systems evolve. It may also help test models of orbital stability and satellite capture. Understanding Nereid contributes to broader theories of solar system dynamics. Nereid's combination of orbital eccentricity, size, and distance make it unique among moons. It sits at the boundary between regular and irregular satellites. Studying it could improve models of planetary formation and gravitational capture. Its role as a possible witness to Triton's arrival offers a rare opportunity for dynamic reconstruction. Iapetus Ridge, a mysterious equatorial belt-like structure around Iapetus, origin still unknown. Iapetus is one of Saturn's most visually striking moons, known for its stark two-toned surface. Measuring about 1,470 kilometers across, it displays a bright trailing hemisphere and a dark leading one. This dramatic contrast was first observed by Giovanni Cassini in 1671. Beyond this, Iapetus also hosts one of the most puzzling geological features in the solar system. A long ridge runs almost perfectly along its equator. This ridge stands up to 20 kilometers high in some regions and stretches over 1,300 kilometers. It forms a narrow band of peaks and valleys, like a mountain range encircling the moon's waist. No other major body in the solar system has a similar equatorial feature of this scale. Its symmetry and alignment with the equator suggest a highly specific formation process, but to date, no single theory fully explains it. The Cassini spacecraft imaged the ridge in detail during its flybys of Iapetus in the early 2000s. The structure appears heavily eroded in places, but remains prominent. The peaks are steep and isolated, with some sections showing signs of landslides. The ridge intersects numerous impact craters, indicating that it is geologically old. It likely formed early in Iapetus's history. Several hypotheses have been proposed to explain the ridge. One suggests it formed from internal tectonic activity, possibly due to cooling and contraction of the moon's crust. However, Iapetus lacks other tectonic features, making this scenario unlikely. Another idea is that material accumulated from a former equatorial ring. If Iapetus once had a ring system, its debris could have settled along the equator. A third theory involves rotational deceleration. If Iapetus once spun faster, it could have had an equatorial bulge. As it slowed down due to tidal forces, the bulge may have collapsed into a ridge. This would require specific thermal and structural conditions. Still, the mechanism has yet to be demonstrated in simulations. All existing theories have unresolved flaws. The ridge's composition appears similar to the surrounding terrain. This suggests it is not made of foreign material. Radar and spectral data do not indicate unusual mineral content. Its uniformity implies that the ridge was shaped primarily by mechanical processes rather than compositional differences. The age of the ridge remains uncertain, but is estimated to be several billion years. The alignment of the ridge along the equator is highly precise. This precision adds weight to theories involving rotational or orbital dynamics. If the ridge formed from a collapsed ring, it would mark a rare example of such a process. Saturn's rings are often studied for comparison, but Iapetus's case involves a different scale and context. Modeling these dynamics is still ongoing. The presence of the ridge may influence local surface temperatures. Its steep faces create long shadows that limit solar heating. Thermal imaging shows slight temperature variations along its slopes. These differences could affect frost deposition and ice sublimation over time. However, no active processes have been detected. Iapetus itself has a highly inclined and distant orbit compared to Saturn's other large moons. This isolation means less tidal heating and fewer gravitational interactions. The lack of recent geological activity is consistent with its cold and static environment. It also limits opportunities for resurfacing, helping preserve ancient features like the ridge. Cratering analysis suggests the ridge is older than many other features on Iapetus. The presence of superimposed impact scars indicates its longevity. However, some sections appear more eroded than others. This suggests varying rates of degradation or past seismic events. Continued analysis is needed to understand these differences. The ridge has not been observed on any other planetary body. Its uniqueness makes Iapetus a key target in comparative planetology. Understanding how such a structure could form informs models of satellite evolution and ring-moon interactions. It also raises broader questions about early solar system dynamics. Further missions would help refine these theories. Iapetus Ridge remains one of the most enigmatic geological features in the outer solar system. No single explanation has yet accounted for its origin, shape, and preservation. It exemplifies the complexity of seemingly simple celestial bodies. Until more data becomes available, the ridge will remain a topic of active scientific curiosity. Triton Geysers. Nitrogen geysers erupting from Triton's frozen surface. Surprising behavior in extreme environments. Triton is Neptune's largest moon and one of the most geologically intriguing bodies in the solar system. Discovered in 1846, it is roughly 2,700 kilometers in diameter. Its retrograde orbit indicates it was likely captured from the Kuiper belt. This capture event would have caused significant disruption in the Neptunian system. Triton's surface is composed mainly of nitrogen, water, and methane ices. During the Voyager 2 flyby in 1989, scientists observed dark streaks on Triton's southern hemisphere. These markings were traced back to active plumes erupting from the surface. The plumes reached heights of up to 8 kilometers, ejecting gas and dark particles. These were the first geysers observed outside Earth, Enceladus, or Io. Their discovery was completely unexpected. The geysers are driven by solar heating of a thin layer of nitrogen ice near the surface. Sunlight penetrates the semi-transparent ice and warms darker material beneath. This creates a pocket of gas that eventually ruptures through the surface. The expelled gas carries fine particles, creating long, wind-blown streaks. These geysers suggest a surprising level of activity in Triton's frigid environment. The mechanism is called solid-state greenhouse or cryovolcanic geysering. It relies on the unique optical properties of Triton's ice. Despite temperatures near -235 degrees Celsius, sunlight can still trigger these eruptions. This challenges assumptions that extreme cold prevents surface activity. The geysers show that even distant icy worlds can be dynamic under specific conditions. Triton's surface is geologically young, with relatively few impact craters. This implies frequent resurfacing, possibly aided by geysers or cryovolcanism. The southern polar region shows layered terrains and smooth plains. Some areas contain cantaloupe terrain, raised, lumpy features with no clear analog elsewhere. These features may be linked to internal convection or surface collapse. The nitrogen geysers contribute to Triton's tenuous atmosphere. This atmosphere is primarily nitrogen with trace amounts of methane. Seasonal heating causes it to expand and contract. Geyser activity may play a key role in maintaining atmospheric pressure. This makes Triton one of the few moons with an active atmosphere-surface exchange cycle. Triton's internal heat may be driven by tidal interactions from its past orbital evolution. Although it now has a stable orbit, earlier interactions with Neptune may have generated internal friction. This residual heat could fuel subsurface melting or gas buildup. The geysers may be a surface expression of these deeper processes. Their distribution may reflect thermal gradients within the crust. Wind patterns observed during the Voyager flyby aligned with the directions of the geyser plumes. This suggests an active climate system, albeit extremely thin. The black material from the geysers darkens the surface, altering local albedo. This in turn influences future heating and geyser formation. The cycle may be self-reinforcing over seasonal timescales. The spatial pattern of geysers suggests a link to the solar zenith angle. Eruptions appear more frequent where sunlight hits most directly. As Triton orbits Neptune, its inclination leads to seasonal changes. These variations may shift the active zones over its 165-year orbital cycle. This provides a long-term dynamic environment despite the extreme cold. No other Neptune moon shows similar activity, making Triton unique in its system. Its captured origin may explain this difference. Kuiper belt objects are thought to retain more volatiles than typical moons. If Triton formed beyond Neptune and was later captured, it would have brought a different thermal and chemical history. The geysers may be a result of this distinct origin. Future missions to Neptune could investigate Triton's geysers more thoroughly. Instruments could monitor temporal variation, composition, and subsurface sources. Understanding the plumes may offer analogs for cryovolcanic processes elsewhere. Triton is a candidate for habitability studies due to possible subsurface oceans. Geysers could provide indirect sampling without landing. The discovery of nitrogen geysers on Triton redefined expectations for activity in the outer solar system. It demonstrated that even extremely cold environments can host dynamic surface behavior. These eruptions offer insights into planetary energy, ice physics, and atmospheric exchange. They remain a high-priority target for future planetary science missions. Pluto hosts an icy heart, water ice mountains, atmospheric haze, and possibly a subsurface ocean. Pluto is a dwarf planet located in the Kuiper belt, about 5.9 billion kilometers from the Sun. Discovered in 1930, it was considered the 9th planet until its reclassification in 2006. It has a diameter of approximately 2,377 kilometers, making it smaller than Earth's moon. Pluto's orbit is elliptical and inclined, completing one revolution around the Sun every 248 years. It rotates once every 6.4 Earth days. In 2015, NASA's New Horizons mission provided the first close-up images of Pluto. One of the most prominent surface features is a bright, heart-shaped region named Tombaugh Regio. The left lobe of this region, known as Sputnik Planitia, is a vast plain of nitrogen ice. It is believed to be a giant impact basin later filled with ices. This basin is geologically active and shows signs of convective movement. Sputnik Planitia exhibits polygonal patterns and cell-like structures formed by thermal convection. These patterns suggest ongoing resurfacing processes despite Pluto's distant location. Beneath the surface, slow churning of nitrogen ice is thought to erase impact craters. This ongoing motion challenges assumptions that small, cold bodies are geologically inactive. Pluto is far more dynamic than previously believed. Pluto's surface features include water ice mountains rising up to 3.5 kilometers in height. These mountains are likely made of water ice, which acts as bedrock at Pluto's frigid temperatures. Overlying these peaks are layers of nitrogen, methane, and carbon monoxide ices. These ices migrate across the surface through sublimation and deposition. The combination of rigid terrain and mobile ices creates a complex landscape. Several dark regions along Pluto's equator are rich in organic compounds called tholins. These compounds form from ultraviolet radiation acting on methane in the atmosphere. Tholins give Pluto its reddish hue and accumulate over long timescales. Their presence indicates ongoing surface-atmosphere interactions. Similar compounds may be widespread on Kuiper Belt objects. Pluto's tenuous atmosphere is composed mainly of nitrogen with traces of methane and carbon monoxide. It forms a thin haze that extends up to 200 kilometers above the surface. New Horizons observed multiple haze layers, possibly due to condensation cycles. These layers scatter sunlight, producing twilight-like effects even in low light. The atmosphere expands and contracts with Pluto's distance from the Sun. As Pluto moves farther from the Sun in its orbit, its atmosphere may partially collapse and freeze onto the surface. Observations from Earth and New Horizons show seasonal changes in atmospheric pressure. Understanding this behavior provides insight into volatile cycling on icy bodies. Pluto's thin atmosphere is a key driver of its active surface processes. Evidence suggests Pluto may have a subsurface ocean beneath its icy shell. Tectonic features such as extensional faults and rotated blocks indicate internal expansion. This expansion could result from freezing of an internal ocean pushing the surface outward. Thermal models support the possibility of liquid water preserved by antifreeze compounds like ammonia. This remains a subject of active research. Charon, Pluto's largest moon, has a synchronized orbit and shares a tidal locking with Pluto. The two bodies orbit a common center of mass located outside Pluto. Charon's surface also shows signs of tectonic activity and cryovolcanism. The Pluto-Charon system behaves more like a binary planet than a typical planet-moon pair. Their mutual interactions shape their orbital and geological evolution. Pluto has 4 smaller moons: Nix, Hydra, Kerberos, and Styx. These moons have irregular shapes and chaotic rotation states. They orbit in near-resonant configurations, which may help stabilize the system. Observations suggest they formed from debris after a giant impact that created Charon. Their properties provide clues to how moons form around small icy bodies. The surface temperature on Pluto averages around -229 degrees Celsius. At these temperatures, nitrogen and methane are solid, forming glaciers and frost. Despite the cold, sunlight still drives slow changes in surface ices. These changes are monitored by ground-based telescopes and space missions. Seasonal effects play a major role in the evolution of Pluto's appearance. Pluto continues to reshape our understanding of what is possible on distant icy worlds. It exhibits geological activity, atmospheric dynamics, and potential for internal oceans. Although it is no longer classified as a planet, its complexity remains scientifically valuable. Future missions may return to explore its surface, interior, and potential habitability in more detail. Oumuamua, an interstellar object that passed through the solar system with anomalous acceleration. Nature still unknown. In October 2017, astronomers discovered an object passing through the inner solar system on a hyperbolic trajectory. Named Oumuamua, it was the first confirmed interstellar object observed visiting our solar system. It was detected by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian. Its speed and orbit confirmed it was not gravitationally bound to the Sun. Oumuamua's trajectory was highly eccentric, with an inbound velocity of 26 kilometers per second relative to the Sun. It passed closest to the Sun on September 9, 2017, and exited the solar system shortly after. Its path could not be traced back to any known star. It appeared to come from the direction of the constellation Lyra. This trajectory ruled out any origin within our planetary neighborhood. The object showed no visible coma or tail, which is unusual for a body on such a trajectory. Most comets heat up near the Sun and release gas and dust, forming a visible envelope. Oumuamua appeared completely inert in optical wavelengths. This lack of activity led many researchers to initially classify it as an asteroid. However, later analysis challenged that assumption. Observations showed that Oumuamua experienced non-gravitational acceleration as it moved away from the Sun. This slight but measurable deviation could not be explained by gravity alone. No outgassing was detected, so standard comet models did not fit. Some proposed that the acceleration could result from outgassing of invisible molecules like hydrogen or CO. Others suggested alternative explanations. One hypothesis is that Oumuamua is a thin, flat object experiencing solar radiation pressure. If its surface area is large compared to its mass, it could be pushed by sunlight. This led to speculative suggestions that it might be artificial, such as a solar sail. However, no direct evidence supports this theory. Most researchers favor natural explanations. The shape of Oumuamua remains uncertain. Based on its changing brightness, it may be highly elongated or flat, with a length-to-width ratio of at least 6:1. It rotated every 7 to 8 hours, creating fluctuations in brightness by a factor of 10. These variations indicate a tumbling motion, not a stable spin. The exact geometry remains unknown due to limited observation time. The surface appears reddish in color, suggesting exposure to cosmic rays and space weathering. Spectroscopy was limited but consistent with organic-rich material or carbonaceous compounds. These traits resembled known objects in the outer solar system. Still, Oumuamua's origin and exact composition remain unresolved. No similar object has been observed before or since. Because Oumuamua was discovered after its closest approach to the Sun, scientists had only a few weeks to observe it. No spacecraft could be redirected in time to intercept or study it up close. All data comes from Earth-based telescopes and a few orbital observatories. As a result, many key properties are based on inference rather than direct measurement. Its interstellar origin was confirmed by its speed and trajectory. Unlike objects from the Oort cloud or Kuiper belt, Oumuamua was not gravitationally captured by the Sun. It will continue traveling through interstellar space indefinitely. Its detection confirms that such objects pass through our solar system, though they are extremely rare. Their study opens a new field of observational astronomy. Oumuamua's passage inspired the development of new detection systems. The Vera C. Rubin Observatory, expected to begin operations soon, will be capable of spotting more interstellar objects. Early detection would allow more detailed tracking and possibly spacecraft missions. Scientists hope to learn more about planetary systems beyond our own. The event raised fundamental questions about how interstellar objects form and evolve. Some may be debris from planetary formation processes in other star systems. Others could be fragments ejected by gravitational encounters. The diversity of such bodies is unknown. Oumuamua was the first glimpse into a new class of solar system visitors. While most theories favor natural explanations, the lack of definitive data leaves some aspects open. Oumuamua remains one of the most mysterious objects ever detected. Its brief visit prompted scientific debate, public fascination, and international research. Future discoveries may help clarify its nature and origin, but for now, it remains unresolved.